Hello, Math 1224. This is Dr. P with Lesson Launch 16.2, A Harmonic Duet. So I've put up here this series, the sum from 1 to infinity of 1 over n, and I've written out the first few terms. In fact, I've written out quite a few terms for reasons you'll discover in just a moment. But I don't know if I've ever mentioned this before, but this series has a special name. This is called the harmonic series, or a harmonic series. I'm not quite sure whether there are several things called harmonic series or just this one. But anyway, that's called the harmonic series. Forgive my poor handwriting there. But anyway, you probably already know whether this series converges or diverges. At least you think you know, because you know that this is a p series with p equals 1, and that's less than or equal to 1, and that makes this series divergent. And there's no trick there. The series is divergent. But sometimes when I speak with students about series, I feel like there are beliefs about whether series converge or diverge based on convergence tests like this one. So something very official sounding like the p-series test. I always wonder whether those beliefs are connected in any way to any intuition about what this series actually does. Because I know that a lot of students that I encounter, and I know that this was true of me when I was a student, I thought, well, look at this series here. The series terms are getting smaller and smaller, 1/5, 1/6, 1/7, 1/8, and they're getting so small that there's no degree of smallness beyond which the terms of this series will not get. I mean, eventually we'll reach a point where every term of the series is below 1/1,000,000th, and eventually we'll reach a point where every term is below 1/1,000,000,000th. And under those circumstances, how in the world could a series like this possibly go to infinity? Because if this series doesn't converge, then that's the other option. If it's all positive terms and it doesn't converge, that means it diverges to infinity. So I just want to do a quick demonstration here with this series here. So I'm going to use a number line diagram to illustrate something, illustrate how the partial sums of this series behave. All right. So I'm going to mark off a few points here. Probably won't even need all of those to convince you that this series really does go to infinity. So remember, the way that we define series convergence or divergence is we look at partial sums. We look at the results when we add up the first few terms of this series. So first we look at what happens when we add up the first one term. Well, the first partial sum is just that first term, which is 1. That's s of 1. And then the second partial sum is 1 plus 1/2. That's 1 plus 1/2 there. That's s of 2. And now I'm going to do something a little bit unexpected. I'm going to skip over to the fourth partial sum. Just skip the third one altogether and look at s of 4, the fourth partial sum, and ask you to notice something. I already have 1 here, and I have a half here. Look at these two terms here, 1/3 and 1/4. I hope that you'll agree with me that those two terms are at least as large as 2/4, because one of them is a fourth, this one here. Let's see, this one here is 1/4, and this one is bigger than a fourth. Actually, that reminds me of a funny story, which is that somebody, I think maybe Carl's Jr., once tried to market a third-pound hamburger, but the product failed because people assumed that the third-pound burger was smaller than a quarter-pounder from McDonald's. That's a story that's often told about people's lack of understanding of fractions. But anyway, this video is going to be long enough without me going off into stories and jokes. So anyway, these two terms together make up at least 2/4, which is at least 1/2. And of course, those two together will be greater than 1/2. But I'm just going to say those two terms will add up to something a little bit bigger than 1/2. And so when I add that to s of 2, I'm going to get that s of 4 is somewhere beyond 2. All right? Now, look at these four terms. So once I've added these four terms, as well as these, and these, I'm going to have s of 8, the sum of the first 8 terms. But those four terms there, those are going to be at least as large as 4/8, which is another 1/2, because a fifth is larger than an eighth, a sixth is larger than an eighth, and a seventh is larger than an eighth. So together, those make up something at least a little bit greater than 1/2. So s of 8 is going to carry me out past 2.5. How much, I'm not quite sure, but I know it'll be somewhere past 2.5. All right, now think about what I might do next. I haven't drawn enough terms of the series to do this, but if I keep going long enough, I'm going to have marked off at least 8/16, 1/9 through 1/16, that's 8 terms. So now if I add that to everything I've already added up, I'm looking at s sub 16, and that chunk is also greater than or equal to 1/2. So S16 is going to be somewhere past 3. I could go on doing this. I could look at S sub 32, and that would be somewhere past 3.5. And S sub 64 would be somewhere past 4. And who knows, maybe they're much closer to these estimates than I'm giving them credit for. But at any rate, the partial sums of this series are going to keep climbing up by at least 1/2 each time. 1/2, 1/2, 1/2, 1/2, 1/2, 1/2. And it doesn't matter the fact that this is taking an excruciatingly long time after a while. I'm always going to be able to advance another half. And that's why this series is divergent. It's because I can always find a partial sum bigger than any finite real number that you might want to specify. So there's no finite limit towards which this thing is climbing. It's gonna surpass any finite limit that I might set for it. Okay, anyway, so that's a little story about the harmonic series. Now, the reason I wanted to do that was to set up the actual purpose of this video, which is to talk about a different series. And that series is the sum from n equals 1 to infinity of -1 to the n over n. So same idea as the first one, sort of, but this time I've got this funny little -1, stop moving around there, okay, -1 to the n over n. So that's going to be, let's see, what is -1 to the first? That's -1, so I'm going to have -1 over 1, plus 1 over 2, minus 1/3, plus 1/4, minus 1/5, plus 1/6, and so on. And my question is, does this series converge or diverge? Now this time, this is, I think, maybe the first series we've dealt with where the terms alternate between positive and negative. We call that, by the way, an alternating series. Alternating series means something very specific. It means that the terms go either plus minus, etc., and follow that pattern exactly forever, or go minus plus, minus plus, minus plus. But they must be perfectly alternating. None of this plus plus minus, or plus plus minus 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 plus minus minus plus plus plus. No random crap going on. It's got to be strictly alternating in order for me to use the test that I'm going to develop in this video. All right? So anyway, that's an alternating series. And we want to find out whether it is convergent or divergent, question mark. Well, now that's an interesting question because I just got done convincing you. I hope that this convinced you that that previous series, the one that's just harmonic with all positive terms, that really does go to infinity. And the reason it goes to infinity is because I can always mark off, there's a 1, and I can always, after that, mark off another half. It might require a whole bunch of terms after that, but there's always another 1/2 that I can mark off. So I'm always adding another half to whatever I've got. In this case, well, this is a little bit different. I'm not necessarily adding on a half because I might be subtracting off something. Probably not going to be subtracting a half after a while, but nonetheless, I'm adding something, and then I'm subtracting something a little bit smaller, and then I'm adding something a little bit smaller still, and then subtracting something a bit smaller still. And I just wonder, if I were to draw a number line and start looking at partial sums, how would those partial sums behave exactly? I don't know. But let's explore and see if we can find out. So my first partial sum is just going to be the first term, -1. That's s sub 1. And then I'm going to add a half to that. That's going to give me s sub 2. S sub 2 is -1 plus a half. And then s sub 3 is going to be s sub 2, that is these two terms here, and then add on this term. That's minus a third. So I'm going to get something like that for S3. And at some point, it's going to become impossible for me to mark these. So you'll just have to follow what I'm doing. For the next partial sum, I add a fourth. That brings me back here somewhere. And then I subtract a fifth. And then add a sixth. Now, watch what's going on here. Every time I create another partial sum, I land in between the two previous partial sums. And the distance between these partial sums is going to gradually close. And in fact, we get to the point eventually where the amount that I'm adding or subtracting on each subsequent term is tiny, because these terms individually, these terms are going to 0. These -1 to the n's, let me write it that way, those are approaching 0. There's no mistake about that. Now that was true of the previous series as well. 1 over n was going to 0, but those terms accumulated in such a way that there was no limit to the partial sums. In this case, though, I don't know. The amount that I'm adding or subtracting is getting so small, and it's getting smaller every time, which means I'm never going to escape this window here. I'm never going to escape the window between S1 and S2, and in fact, after that, there's going to be this window between S3 and S4 that I'm never going to escape. And those windows are getting smaller and smaller. Let me see if I can zoom in here, make this illustration a little bit better. Okay, now it just doesn't really look like anything. These little pin markings don't happen with infinite resolution. But anyway, the idea is that I'm successively creating these smaller and smaller windows whose size is going to 0 because the term size is going to 0. And eventually somewhere in there, let me see if I can mark this, there's going to be some magic number that these partial sums are going to approach. So the upshot of all this is that still visible? Just barely. The upshot of all this is that these partial sums, okay, now I want to mark, there we go. The partial sums, S sub n, do have a limit in this case. So that series, the sum from n equals 1 to infinity, negative 1 to the n over n, that does converge, whereas the other one diverged. So what made it possible for this one to converge is that I had an alternating series here, so that when I kept taking successive partial sums, those partial sums bounced from here to here to here to here, and they bounce back and forth because the signs alternate like this, this pattern in particular in this case. Back and forth, back and forth. And in that backing and forthing, my steps are getting so much smaller over time that eventually the window into which these partial sums can fall collapses to a single point. That's a very sloppy mathematically way of putting something that you would learn about in a real analysis course, but that's kind of the idea. And that's happening all because what I'm dealing with is an alternating series that satisfies certain conditions. So I want to formalize what those conditions are, because there's a way that you will typically write up a problem involving an alternating series if it is a converging alternating series. By the way, not all alternating series converge, and it's important to realize that. But there are certain conditions under which you can say absolutely an alternating series will converge. Actually, I shouldn't say absolutely, because that means something very specific. And not all alternating series converge absolutely. Sorry, I probably shouldn't have even said that. That was a little bit off message there. But there's an alternating series convergence test. And here's how it goes. Suppose I have a series, A sub n is a series such that the following conditions hold. Number one, the signs of the A sub n's alternate. So either plus minus, etc. Or minus plus, minus plus, minus plus. It's okay if they do that eventually. It's okay if you have a few aberrations at first, like plus, plus, minus, and then you settle into plus, minus, plus, minus. Eventually is enough here. So I'll just say alternate eventually. Usually you see an alternating series problem, it's just going to alternate. It's not going to be an eventually alternating situation. Number two, the magnitudes absolute value of A sub n are strictly decreasing. So in other words, let me just use this as an example here. When I look at this series here, the magnitudes of the terms, well, they're the same as the ones in the harmonic series, 1, 1/2, 1/3, 1/4, 1/5, and so on. And we know that those are always decreasing. Okay. To put this a bit differently, here's a more algebraic way of putting it. That is, absolute value of A sub n plus 1 is always less than absolute value of A sub n for every n. Sometimes you'll be called upon to prove that. All right, and finally, number three, last but definitely not least, the limit as n goes to infinity of the absolute value of A sub n is 0. So in other words, the magnitudes of the terms need to be approaching 0. It's not enough for them to just be decreasing. They've got to be decreasing towards 0. So again, let me zoom out here and use this other series as an example here. So in this case, I've got a series. It really is alternating. It goes minus, plus, minus, plus, minus, plus without fail. The magnitudes are strictly decreasing, 1, 1/2, 1/3, 1/4, and so on. And those magnitudes are approaching 0. That is the magnitudes of the individual terms. If I know all of this, if I know these three things here, then I can say this. If I know all three of those things, then the series, the alternating series of the a sub n's from n equals 1 to infinity, this series converges. All right? And that's a theorem there. And the idea of the theorem is based on what we just talked about with this number line here, that now, it may not be this particular number line diagram because you might have different series terms with different sizes, but the idea always is your partial sums, like if you had a zeroth partial sum, it would start at 0, and then you start bouncing back and forth by adding terms. You might bounce forward and then backwards and then forwards and then backwards again, but because you're bouncing back and forth in a very organized way, and your jumps are getting smaller and the jump size is approaching 0, eventually you're going to reach some limit. You're not eventually going to reach that limit, I shouldn't say that, but there's going to be some limit that you are always trending towards. And that's the idea of the alternating series convergence test. Or sometimes people just call it the alternating series test. Nothing wrong with that. Okay, now I mentioned the word absolutely earlier, and then I had a major sort of fumble over that. So let me explain what that was about, because that's another important idea. So this is a definition, and we probably won't go into great detail on this, but it's something I want you to know in case you ever take other math courses, like an engineering mathematics course, where you might talk about whether things converge absolutely or not. So what does absolute mean in this context? A series, a sub n, I'm just going to leave off the indices. So imagine that going from n equals some number to infinity. It doesn't have to be 1. A series converges absolutely. Converges absolutely if the series consisting of the absolute values of the a sub n's converges. Now that would be a series with all non-negative terms. All right, so if this series converges, then we say that this series converges absolutely. And actually it's a theorem that if this converges, if the series of the absolute values converges, that implies that this also converges. So that's why we're willing to say, oh, it converges absolutely. Okay, on the other hand, if this series converges, a sub n, if that converges, but the series of the absolute values of the a sub n's diverges, then we say the series of the a sub n's converges conditionally, which I always thought was kind of a weird term, converges conditionally. I always thought that was kind of a weird way of saying something, because, I mean, if this converges, so imagine this being like an alternating series or something. Sorry about dragging the screen around. The tool for this little laser pointer and the tool for dragging the screen around look an awful lot the same, so sometimes I mix them up. Anyway, imagine this being like an alternating series or something. So maybe this converges, like that one that we were just talking about earlier, the one with the harmonic series terms along with the alternating plus and minus signs. So that's an example of this converging, but the sum of the absolute values of those terms definitely does not converge. Then we say that this converges conditionally, which is weird because, I mean, either something converges or it doesn't. It's not like, well, it'll converge if it's raining tomorrow or something. That would be an example of conditional convergence. Or, it'll converge if I feel like it. That would be conditional. But this really does just converge. But in mathematics, we recognize a connection between this series, its terms, and the terms of this series, and the behavior of these two series. And sometimes we're interested in whether an alternating series converges just because it had the advantage of going plus minus, plus minus, plus minus, or if it would have converged just by virtue of the terms of the series being small enough. That's kind of the idea of absolute versus conditional convergence. So again, just to summarize, I know I'm about to back into 20 minutes here. This is a no-no when it comes to this medium. But the idea, or the moral of this video, is that this is a series here, this one right here, That is a conditionally convergent series because it converges by the alternating series test, but its cousin, this dude right here, does not converge, the one with all positive terms. Okay, anyway, that's it. One more video after this, and then we'll be ready for class. Hopefully a shorter video. I'll do my best anyway. Stay tuned.